Okay, now we can start. Okay, you guys ready in the back? Can you hear this okay? How's the audio in the back? Thumbs up. Great. Okay. So good afternoon. My name's John Owens. I'll be teaching this course. Thank you all for coming. I know there's some auditors in here. You're welcome. Please come and please participate is really the big thing. We're hopefully going to cover a lot of good material. We have some wonderful guest speakers this quarter. So I'm very happy to have you all here, those of you that are enrolled and those of you that are auditing. And please ask questions throughout. It will make a better course for everybody. Let me tell you a little bit about myself to start off. I have been at Davis for 7 years. I'm an associate professor in electrical and computer engineering. I've taught this course every year that I've been here. So hopefully that means it'll run a little smoother than if this was my first time. I'm going to have an office hour in my office every week. You just missed it, so I'm sorry about that, but I'll be back the next week. What I understand usually happens is people make appointments with me or drop in at other times. Rarely do people actually come during the office hour. One thing I will admit is that I'm teaching another course at the same time. Not at the same time. I'm teaching another course this quarter, which is an undergraduate course on digital design. It's probably going to have it has more students, and they're going to come to my office hours a lot more, so you're going to have to fight with them. So anyway, please feel free to email, drop by these office hours at any time, or email and let me know that you'd like to chat. We can do instant message kind of things if that's easier. You're all graduate students, or most of you are graduate students, so we can communicate in any sort of way you find interesting. My PhD was at Stanford. At Stanford, I did work on the Imagine Stream processor, and we built computer graphics as part of that. That was the topic of my dissertation. So that's sort of my hardware background, that we built a processor. The current research that we're looking at is using GPUs for general purpose uses. So you've got all this arithmetic horsepower on a GPU, and what do you want to do with it that's not graphics? And that's sort of what our group's good at. It's very much an emerging trend and one that's getting a lot of momentum. And so over the years I've taught this course, there was nothing about that at all when I started teaching this course. And as the years have gone on, this has become more and more interesting and more part of graphics architecture and what people are doing with GPUs. So it's becoming a bigger part of the course. We're certainly going to have a good amount of course material that uses that. So that's hopefully useful skills, even if you don't do graphics or graphics architecture in the future. Knowing how to do a little parallel programming and how that works in the context of a GPU will hopefully be interesting for you. Okay, so here's what I'm going to talk about today. I'm going to start with sort of high-level technical material, and I'll talk about why I think graphics hardware is interesting. And why I'm excited about this material, and hopefully why you guys will find it interesting too. And we'll sort of talk about some history, sort of what have people done with graphics hardware in the past, how did it start, and what are sort of the new features that have come in as time has gone on. So giving you a high-level view. Then I'll do a class outline. I'll sort of have one slide for every lecture that we're going to do, so you know the sort of things we're going to cover in the class. And at the end, we'll talk about administrative sort of things. If I were you, so I'm not going to do any handouts the whole quarter, so nothing for you to take home. There is a smart site with a syllabus on it and a schedule, and that's where I'll be posting assignments and where you'll be turning things in. I haven't used Smart Site before. How many people in here have? Okay, a few. So this is sort of the university system for doing course-based web pages, project-based web pages going forward. And it's a centralized thing, so they serve all of campus. It's basically a web system and a web hand-in kind of system, and it will do all of your course needs. I'm certainly interested to hear about what you like about it and what you don't like about it. I have been vocal in saying the things that I don't like about it, and we'd like to be able to give feedback to the people that build it so it'll get better in the future. Okay, so why graphics hardware? So one of the reasons that graphics hardware is very interesting is that it has a very high growth rate compared to CPUs. And so roughly a few years ago, CPUs stopped getting faster. Okay, you know that 5 years ago you could buy a 3 gigahertz GPU or CPU. Today you can buy a 3 gigahertz CPU. And now it's got more cores and so on. But basically the performance of a single core has not really changed in the last few years. What is changing is the performance of graphics processors, and it's because graphics processors do an excellent job of taking advantage of parallelism. And so that's really one of the biggest themes in this course. Parallelism is very much on the minds of computer architects, system designers, system software people. And how do you use it effectively is something that we're really going to spend a lot of time in. So this is a little bit old because it's Pentium 4 data here. The red circles are sort of showing how spec floating point performance has grown over time. And so 30% a year. Okay, not so bad. But then you can look at some graphics style metrics. You can look at fill rate for NVIDIA processors. And what I'm showing there is how many pixels you can process per second. You can look at geometry rate, which is how many triangles you can process per second. And those are things historically that have been growing at a much faster rate than you see CPU performance. Okay? So one thing I want you to understand by the end of the class is why. Why do we see these sort of growth rates looking really good? And GPU people have done a very good job at keeping on these historical growth rates. Hopefully we'll learn why. And this is why people really are interested in using GPUs, not just for doing graphics, but for doing more general purpose work. Because if we can stay on this performance curve, obviously that's a good curve if your application fits in this sort of area. Okay. The other thing that's interesting about this graph is that you see this performance going up and up and up, and that's really great. And you say, hey, that's great. But if you think back to your CPU that you were using 15, 20 years ago, okay, what could it do that your CPU today, what can you do with today's CPU that you couldn't do 15 years ago? Okay, the answer is not much, right? If you went and bought an original Pentium in, I guess, 1994 or so, okay, what can the Pentium do that today's Core 2, or what can the Core 2 quad do that a Pentium can't? It's not very much. Whereas if you look at the graphics processors here, okay, graphics processors today do things that even graphics processors 3 or 4 years ago couldn't do. That they're getting these historical, performance increases and they look great, but they're also adding all these features at the same time. Okay, so it's great for if you're using GPUs, but it's also really interesting if you're building GPUs. How do you do that? How do you get these performance increases and be able to introduce all these new features? And that's why I think the graphics architecture part of this course is really interesting. Okay, so the other figure of merit that I'm sort of wanted to go over was, and I'll show this graph more than once in class because it comes up a lot, is just how much performance can you get out of a GPU? Sort of, what's the raw amount of performance? And so what we're showing here in blue is sort of maximum performance you can get out of an Intel microprocessor. And so you'll see a couple jumps in this graph. There's a jump here where we went to dual core machines from here to here. There's a jump where we went to quad core machines. Sort of, if all you're doing is floating point operations over and over and over again, how many can you fit? So with a quad core machine, you're getting roughly 100 billion floating point operations per second, which is pretty good, and better than it was a few years ago. What we see with the GPU graphs, the NVIDIA GPUs in green and the AMD GPUs in red, is that we're getting almost an order of magnitude more. And this is why people are interested in using these not just for graphics but for some other things. But the performance curves are also very good. This is something that doesn't really look to be leveling out. And it's something else we'll be discussing in this class. How do you build these things so they continue to be scalable into the future? And it really is a phenomenal amount of performance that you can throw at the problem for a relatively low cost. So sort of the figures we have over here, and this is maybe a month old, but how much does it cost to buy one of these GPUs or CPUs? So roughly the cost of a CPU and the cost of a GPU, pretty much equivalent. It depends on when they come out and how much they cost and so on, but roughly they're equivalent. One thing to keep in mind, though, is that when you buy a CPU, you get a chip. When you buy a GPU, you get a whole board. It has not just the processor, but also memory and display hardware and other things that come along with that. So it's not quite an apples-to-apples comparison. The other figure that I have up here is bandwidth. So how much can you get out of the memory system? Okay, so if you go buy a front side bus of, I don't know, whatever the fastest one is today, you can get 12 gigabytes a second from the memory into the CPU. Okay? But a GPU is very memory hungry, and they're willing to spend more money on memory hardware. They have wider buses and so on. And so you're also looking at having an order of magnitude more data bandwidth to play with. So for people that want to do high-performance computation, having 10 times as much performance and 10 times as much bandwidth is really a very welcome thing. So again, we'll be talking about why some of these things are in the course of this class. Any questions on these? Cool. Okay, so why am I excited about this, this material? Well, first, I think graphics in general is a really interesting problem. So, there's lots of different things you could be spending your time doing, lots of different application areas. You could be doing artificial intelligence or scientific computation or databases or many different things. I think graphics is really important. And the reason I say that is that we interact with the world through our visual system. And it's sort of the highest bandwidth path into our brains. So it's very important we do a good job with graphics. And it's an increasingly important thing in the way we interact with computers in general. When I started teaching this class, everybody had these nice 2D desktops. But now most of you that have laptops have this nice Windows or Mac Quartz interface, and there's some cool 3D stuff with that. Or Windows has Aero Glass now, and so hey, that's a pretty neat, nifty thing that we're moving toward more 3D kind of interfaces. Hey, that's cool. New ways to present information. That's very important. And we're in a world where the amount of data that is generated is growing astronomically. And how do we make sense of that? Well, we make sense of that through visualization. How do we view this? And if we do a good job with our visualizations, we can interpret more data than we ever could before. So graphics is really the core of all that. Plus, there's lots of you that are interested in graphics because graphics is fun and you can do cool things with it that have nothing to do with work or data analysis or anything like that at all. So I often get students in that are really avid gamers. It's great because I'm not. But you can offer perspective on some of the things that we're talking about. Like, oh, this feature's really interesting. This makes a big difference in terms of 3D immersive environments, which are people running around shooting each other. Okay, both from a hardware and a software point of view, the algorithms that we do in graphics are really interesting. So for me, computing courses eventually come down to algorithms. What are neat algorithms to be able to solve problems? And I think the algorithms we use in graphics and the ones I'll talk about that we implement in hardware are really cool algorithms, really neat ways to solve the problems that we see in graphics. So what are those algorithms and how do they map onto hardware? Something we'll spend a lot of time on. Graphics architecture is interesting because of the implications it has not just in graphics, but on system design in general. And so this sort of parallelism idea that we're seeing, why do we have these performance growth rates that we do? Well, it's because GPUs are doing a great job taking advantage of parallelism. Okay, well, parallelism is interesting for all kinds of applications now. Everybody wants to go parallel. We have 2 or 4 cores in every CPU that we see now. We're going to see more and more in the future. Everybody wants to go parallel. What can we learn from that? What can we learn from the way that graphics has chosen to do it? One thing I will talk about in the class is sort of the difference between latency-oriented computing and throughput-oriented computing. If you build a CPU, you're really interested in reducing latency as much as you can. That's what you really care about. Okay? And so you have all these hardware structures that let you do that. So you have all these caches, so you don't have to go out to memory. Instead, you can get things a little bit closer. You have these very sophisticated, branch prediction schemes so that you don't have to wait for a branch to resolve and you can continue to make progress. You have all these forwarding paths in the hardware and so on. So your goal is to minimize latency because you care about the performance of one thread. You want that thread to finish as fast as possible. Okay, graphics does something different. Graphics doesn't really care about how long it takes for you to render one pixel. What it cares about is how long it takes for you to render all the pixels. Okay, and it's a different way of thinking about the problem. What it cares about is throughput. It cares about how many pixels you can do per second. And there are many implications to having that different focus. And so more broadly, there are many problems that care a lot more about throughput than about latency. Okay? And I think in the future we'll see in any computer system some latency-oriented processor cores and some throughput-oriented processor cores. And so the GPU is sort of at the forefront of this throughput-oriented trend. And so we'll talk about sort of how that's different than what you see in CPUs. Okay. Programmability is something that I think is very interesting. If you look back at a graphics processor 10 years ago, there really wasn't a lot of programmability you could do. You could sort of configure it. You could change some knobs. But you weren't really able to program it, more like a general purpose processor. Over time, what's changed is just recently this addition of more and more programmability to the graphics processor, and it lets us do more sophisticated shading and lighting kinds of things. So how do we support that in hardware? How do we add programmability to this fixed function pipeline? And then what's the programming model look like? What should the view that the programmer has of the machine, what does that actually look like? And that's something that's changed over time, but it's very important because this is something that can support a lot of data parallelism and something potentially that can have really good performance. And finally, this moved toward GPU computing, using GPUs for not just graphics, but also for other things. And this is what we do our research on, so I can speak with a little bit of authority on this. But this sort of possibility is why a lot of people are really interested in this topic as well. OK. So now that's sort of a high-level view of why I think this problem is cool, and hopefully why you'll think this problem is cool, and we can keep this room full for the whole quarter. I'll talk a little bit about how graphics hardware has evolved over time. And so sort of the earliest systems were the software-only systems. And so whenever you develop something new, you want somebody that's willing to pay a lot of money for a really crummy system. And so the answer to that question is usually the government. So what the government really cares about, or the government's defense contractors really cared about, the first thing people were really interested in is building flight simulators. That makes a lot of sense. You're willing to pay a lot of money for a flight simulator because it's even more expensive to crash a plane. So hey, if we build these flight simulators, we're willing to pay a lot of money for them. So some of the cool things about these systems. First, they were done with software only. There really wasn't any graphics hardware, and that's why it's generation 0 instead of 1. One of the characteristics was that it was a vector display, not a raster display. And so let me sort of distinguish those things. We're usually used to a raster display. Okay? This monitor, this computer, is a raster display, meaning that it's got a big grid of pixels, and you can individually change any of those pixels. Okay? And so the way that a raster display is scanned out is that you've got some sort of beam that just goes just runs over every scan line. Okay? And does that 60 frames a second. Okay? So it redraws the whole frame every time. So vector displays look more like a radar screen where you see little dots on it. That has a beam that moves and draws lines and so on. And so it's a very different kind of display. And that's the earliest systems were these vector displays. And part of the reason for that was that if you have a raster display, you have to be able to store the entire image in memory at the same time. And the data structure you use that we'll talk about later is called a frame buffer. A frame buffer is sort of a data structure, a big grid of pixels that will store all the colors of those pixels. And so that amount of memory to store an entire screen's worth of pixels was really expensive. And so it's $20,000 at the time. And that was $20,000 for each color. So if you wanted red, green, and blue, that was $60,000, which was tons of money. And so nobody really wanted to build that. Instead, if you had a vector display, then you didn't have to store all this. And so there's a lot of cool graphics techniques meant to not use a frame buffer. And so at the time, this was this enormous bottleneck. And so we're very lucky to be living in a time where the amount of memory it takes to store an entire frame is ridiculously cheap. But it was not always that way. OK. The other cool thing they did is, as they started to move to raster displays and they kept building flight simulators, they still couldn't afford to have all this memory, so they used a technique called beam chasing. So I talked about the way the raster worked, that it starts up at the top and it just runs down every scan line, okay, over and over and over again. And so they didn't have enough memory to store the whole screen. So what they would do is the beam would be running here, and their computation would try to stay ahead of the beam. And they would compute the pixel value they needed to compute right before the beam got there, and then try to stay ahead of that best they could. So it was like a guy running away from a crocodile, right? It's always right on your tail. But then the only memory you actually need in the system is enough between the beam and your computation. And if you can stay ahead of that, then you only need this tiny amount of memory. Okay? So you can envision that would be kind of complicated to get right. You'd really have to get it right, because if you fell behind, you're really hosed and things go wrong in a very bad way. But it was an acceptable technique at the time. OK. So sort of the first generation of machines, a lot of this comes down to a guy named Jim Clark. And so he founded a company called Silicon Graphics, which was very famous, did many graphics advances, and many of you might not have even heard about it because they've been irrelevant for many years now. But they sort of pioneered many, if not most, of the early graphics techniques. And so he was a faculty member at Stanford, and so he and some of his grad students built a geometry engine. And so this geometry engine was a piece of hardware that allowed you to do real-time sort of wireframe style drawings like the one we see here. When I say wireframe, it's sort of a skeleton. you're able to do sort of the lines, but you didn't have the power to be able to fill them in. So still very useful for CAD kind of drawings, and people found it useful for all sorts of things. What this required was the ability to do floating point computation on one chip. And so we'll talk about this particular organization later in the class, and they really didn't do a lot of floating point computation per chip. It was very expensive to be able to do that. But he was sort of the first guy to take floating point, put it on a single chip, organize it in a graphics pipeline such that he could do this sort of thing in real time. So anyway, SGI got to be a very successful company. They were selling the best stuff for many, many years, probably 20 years or so. And so they started building workstations here. They were expensive, but they were the only people in town that could really make this work. Okay, so drawing skeletons wasn't quite enough. What we actually wanted to do was sort of fill them in. So let's fill in some solids here. Okay, instead of just drawing the wireframe and the outlines and just drawing vertices and lines, we're going to try to do fill. And so that requires a lot more work. If you look at how many pixels are drawn here, it's far, far fewer than you had here. And so whereas the bottleneck here was how many triangles per second or how many pieces of geometry per second you could do, the bottleneck here is much more how many pixels per second you can draw. And we'll be spending a lot of time talking about this sort of trade-off between geometry rate and fill rate. Here the problem was fill rate, but SGI again pioneered doing rasterization fill hardware, so hardware that will actually fill in all those pixels. It required that you do lighting at every vertex, so this is made out of a bunch of points, vertices, and you had to compute the light value at every vertex, and the picture we have here uses smooth shading. So we'll see the difference between smooth shading and other kinds of shading, but if you have a red and green and blue and you have to rasterize that particular triangle, well, in the middle it's going to be some sort of gray, and it'll be a nice smooth blend between the vertices. So that was part of the second generation of hardware here. Okay, so the next thing we wanted to look at is, okay, well, we're not just going to do smooth shading anymore. We're not just going to do the sort of fill stuff. We would like to take what we call a texture map, some sort of picture, and map it onto this geometry. So you can think of that as some sort of decal, and you're sort of applying this flat picture onto some geometry. So here we have a picture of some stones. We can sort of wrap that around the this particular piece of geometry and make it look like that's what's actually on the surface. So this is called texture mapping. Okay, texture is the picture, and mapping is the procedure of being able to sort of slap it on this geometry here. And it turns out to be an incredibly useful technique. It's not just useful for putting a picture on a bunch of geometry. It turns out people use it for many, many things that have nothing to do with just pictures. It's a very useful mechanism. We'll talk about how it works here. So what this required specifically was that if you want to do this right, and you actually have to compute the texture value at every single pixel. And to do that right requires that you have to do a floating point divide at every single pixel, okay, to get it right. And a divider is fairly expensive. And to be able to have divides that happen on a full screen 60 times a second, okay, that was a big task. So again, SGI built the first hardware to be able to do this. Today you look at this and say, what's the big deal? My $10 GPU does that, and that's true. But that was a really big deal in 1992. It was very expensive hardware. Okay, so where we're at now is a slide that will not advance, which would not be so good. There we go. Okay. That we looked at this sort of picture here and we said, okay, well, that's interesting because it's just a picture. We'd like to do some more sophisticated thing. Okay? We'd like to be able to program what the surface is going to look like as a program. Instead of just, okay, I can apply this texture and use this light, I can write an arbitrary program. And so if you go look at, say, Pixar movies, which are sort of the gold standard of what things look like today, Pixar movies look amazing. Okay? And the amount of work it takes to make a Pixar movie is far more than it takes to make a real-time scene. And the main difference there is the quality of the shading and the lights that are applied to the objects in the scene. Okay? So we can do simple things like this, a little wood grain, and maybe that's 100 lines of code, 100 operations that we do on every pixel. If you look at Pixar kind of movies, they have shaders that are tens or hundreds of thousands of lines of code long. Okay, so one of the nice parts is we're a long way, there's a lot of room to run. There's a lot of advances that we still would like to be able to make with GPUs. So, but this is a good start, and where we're at with GPUs now is a good start, and you can build real-time games now that let you run 100 or 200 or 300 operations on every single pixel. Okay, and that's pretty cool. And you can make, the reason that games look so much better today than they did 5 years ago is people are using this programmability in really new and very interesting ways. And so this really changed the way that the GPU looked. Before it was sort of this very fixed function pipeline. Now we have to figure out how do we put programmability into that pipeline. Okay, and we'll certainly talk about this in great detail. And if you go buy a GPU today, you're very squarely in this sort of generation. Okay, so where do we want to go? Okay, this is not the end of the road. One potential place we could go is to look for effects that we don't do very well with today's hardware. So I think this picture is a gorgeous picture. This is a rendering of a house with some very interesting lighting. It's by a Dutch architect named Mies van der Rohe. And so if you look at the sort of light effects that you have here, okay, these are fantastically cool light effects. And you look at all the interesting reflections that you see on a semi-reflective floor and sort of a light highlight that you have here. And you look at where the highlights are and like, okay, that's very complicated. And so one thing we don't do in graphics processors at all today is sort of model the light transport, model the way that light bounces around the scene. Okay? Hey, that would be, if you think about let's build a rendering system from scratch, it would make sense to model the physics. Say, okay, well, what really counts is light. And light comes in from these lights and outside there, and it bounces around the scene and makes these colors. Bam, we're done. Okay? Well, there are rendering systems that are built that way. They are just not rendering systems that are done in hardware. So if you buy a software, what's called a ray tracer, then it can do these sort of effects. But that is not the way GPUs work. Okay, and we'll sort of talk about that a little bit. I'm not an expert at ray tracing at all, but you would think moving forward, hey, we'd like to be able to do more sophisticated lighting kind of effects that are closer to the way the natural world works. Okay, maybe that's what comes up next. Okay, maybe we look at how people are building, Pixar movies right now, and we try to do the sort of interfaces that they're doing, make things look like that. That's a different pipeline than graphics hardware uses today. Okay, so there's a lot of places where you can go. You can look at games and say, oh, that looks pretty cool, but you can usually look at a game and be able to tell easily that it's not a picture. Okay, and the question is why, and what can we do to make that better? Okay, any questions on sort of the generations I'm talking about here? Use the mic. Just close.
Curious about that company you said that pioneered all this stuff.
Okay.
Why did they go down? Or why did they disappear?
So I'll be interested to hear from some other people here. Let me draw a little picture. All right, here's what I see as the problem. Okay, it's this pyramid. Okay, this is us. Okay, we have very high demands. We're willing to spend more money than many people on our graphics hardware, but there's not as many of us. Okay, this is my grandmother. Okay, she is willing to buy only the cheapest GPU that is out there. She doesn't really care. All she does is run, Netscape or Firefox and Microsoft Word and so on. Okay, so the problem is that there's a line between people that don't care very much and people that do care. And so the cheapest GPUs you buy get better and better every year. And this line moves up. Okay, so today you can get Intel built-in graphics and it costs $5 to an OEM. And it's okay for 20% of the people in the world. Well, next year Intel makes another one and it still costs $5, but now it's okay for 30% of the people in the world because it does new cool stuff. Okay, there's a point where if you're not doing really cool 3D graphics stuff, Intel built-in graphics are probably good enough for you. So the problem with SGI, at least the way that I see it, is that this line moved up. And it moved up and it moved up, and they had these very talented engineers working on these awesome products, and you couldn't pay them all if you're only going to sell 100 machines a year. Particularly, I think what SGI did a bad job at, I worked there for a summer, so I have a little insight, is that there came a time when you started putting GPUs in consumer machines. All of you buy any sort of computer today, you get a GPU with it. That was not always true. Okay, it used to be you could maybe buy a 2D graphics card and it would, but it wouldn't do anything 3D. Roughly around 1995 or so, people started buying GPUs for consumer-grade things. And so companies like NVIDIA and S3 and ATI came out, and that's what they sold. SGI didn't sell those things. And so these guys are selling 10, 20, 30 million a year, and SGI is still selling 15 huge workstations to big customers. They just couldn't keep their engineering staff going. They didn't have the volume. Anybody else want to offer perspective on this? There's people in this room that have been in the industry longer than I have, and any take on this? Okay, that's my 2 cents. Maybe Wikipedia knows everything, so I'm sure it's there somewhere. It'll tell you all about it.
I'm just curious. They must have had the algorithms and software. Were they able to effectively put it on a chip or kind of transform the algorithm into an effective chip? I mean, processing was moving at a faster pace, right?
So you mean for SGI?
Yeah.
Okay. Right. So, I mean, what they were really good at is building something in hardware that was much faster than anything anybody could do in software. And they continued to innovate year after year and have, a lot of the features we'll be talking about in the class are things that they innovated. But they sort of went up to this generation 3, and this was something SGI did very well. This was something that was done by NVIDIA and ATI and companies like that. This is not something that SGI ended up doing. So when I started graduate school in 1995, we counted how many companies there were. And there were 20-something companies making GPUs of some sort of thing. And so the market does not support 20 different things. And so, partially it's great technology, and some companies had some really good technology. Partially it's did they make good business decisions. So for NVIDIA, for instance, there's a lot of things they do that are wonderful. Their first chip was a total dud. Okay, it was awful. Nobody bought it at all. But the smart thing that they did is they had raised enough money where they could build 2 chips. They failed on their first chip. They had enough money where they could buy the next chip. Some of their competitors didn't have that luxury. They messed up on their first chip and they went bankrupt. I mean, that's true among, if you look at microprocessors. When I was an undergraduate, you could buy computers from Digital with MIPS in them, and you could buy Sun workstations with a SPARC station. And today, x86 is really all it's at. If you look at people that build GPUs for mobile phones, okay, today there's still several companies that do that. But if we took this class 5 years from now, there's still going to be 2 or 3, and that's going to be it. So, I mean, there's a natural consolidation that's going to happen.
Is there any reason why SGI did not jump on the programmable hardware way to go?
Well, I think, okay, 2 things. One is, why didn't they make things that were programmable? And 2 is, why weren't they the technology leader? So if you look at some of their machines that they had planned that they never got to build. So they had a machine internally, it was called Bali, B-A-L-I, because they were expecting when they finished the machine, the company would reward them by sending them to Bali. Awesome. So that machine had a lot of really cool programmable parts. Never really saw the light of day. So they tended to lead with the high end. They put the coolest new features in the high end machines. And the problem was, by the time they got to the point where they decided, are we actually going to build this or not, they didn't think they had the market to be able to support it, and they didn't have the financial structure to be able to do it. Part of the issue is, can you do a good programmable standard? But part of the issue is, can you build a programmable standard that the world's going to like? And by the time programmable hardware was possible in 2000 and beyond, the people that were really leading were these mass market commodity people like NVIDIA and ATI. And they were really the only ones that could have come up with a new standard that would be widely accepted.
They have their own processor, like NVIDIA is also attached to software, the Intel or AMD processors, right?
By and large, they're agnostic. I mean, they would go over originally PCI, then AGP, now PCI Express. I would say most, and people in this room would probably have experience with this, most times if you buy a GPU, it's going to work in any machine. I mean, they would be dumb to cut their throats and not make it work on something. So in general, it was separate from the processor. Yeah?
Physics processing units, PPUs.
Okay.
Yeah. How did NVIDIA manage to integrate them into their GPU?
They
framework?
bought a company called Aegea. Okay, well, I'll give my 2 cents on that, too. So there's interest in building, and I mean, this is an interesting topic because it's something that's increasingly done on GPUs. Okay, we do a great job of modeling the way light works in the scene. Can we model physics, too? Okay, if I have bowling pins over there and I roll a bowling ball, are they going to work in an accurate manner? Well, it turns out that's a very computationally intensive thing to do and do correctly. So, hey, maybe we can build a physics processor. So several companies tried to do this. In general, none of them worked. In my view, the reason none of them worked was because there's a fundamental problem, this chicken and egg kind of problem when you're building a physics processor, which is that you want to build a physics processor that's going to work in all these games, and then it'll make all the gameplay great. But none of the gameplay people want to write anything for your physics processor until it's popular, because why are they going to go to all that work if nobody's going to use it? And then nobody wants to buy your processor because it doesn't work in any games. Okay, so it's kind of a very difficult problem to be able to solve. So the other problem was that nobody could build any games that required a physics processor. So all of us decide to go play, World of Warcraft 8, whatever the new one is. And I have a physics processor, and none of the rest of you have one. Well, my gameplay can't differ from any of yours. Okay? I can't blow up a barrel, and it's going to put shrapnel all over the scene, and I think all you guys died because of that. But you don't have the physics processor, so my view has to be exactly the same as yours. So what it meant was that physics processor companies could only make things that were eye candy. They could only make effects that visually looked good but didn't affect the gameplay. And that wasn't very interesting. People didn't want to buy the game just for eye candy. They wanted physics where they actually manipulated objects and so on. But the market penetration wasn't really there. So what's happening is basically software solutions. So you can do a software-only thing like Havoc, which is a company that Intel bought, and that's all done on the CPU but is moving to the GPU. Or you can buy a company and try to integrate it like NVIDIA did. NVIDIA bought a company called Aegea, and so they're making that work on the GPU. Over time, you'll see more and more functions move onto the GPU, but I think the PPU, as it is not a viable alternative. Okay. So what do we look at moving forward? What changes from these generations? Well, certainly one thing that'll change is performance, and you know that. You know that every time you buy a new GPU, it's faster. And how do we usually measure that? Well, we measure geometry performance and rasterization or fill performance. So how many pieces of geometry we can process per second and how many pixels we can do per second. Also, what changes is features. So things that you can do that you couldn't do before. Okay, hidden surface elimination is that when I put this hand in front of this hand, you want to render this but not this. Okay, that wasn't always part of graphics hardware. Okay, and so it took a little while for that to be introduced. Texture mapping. Okay, there's lots of features that have been introduced over the year, and also quality. Things just look better, and there's many reasons why. For instance, 10 years ago, a lot of rendering used to be done with integer. Today, you do it with floating point. You have more accuracy to deal with, more dynamic range. That's going to make that addition in precision and dynamic range is going to give you more quality. Okay, so these are things we can look at going forward. Okay. So the upshot is that things get faster over time. And so that's exciting because you can have these scenes that only a few years ago would not be able to render real time and would take seconds or minutes or days to render. And then over time, as you get more compute power, better GPUs, more features, it goes from rendering in days and hours to minutes and seconds. Okay, and eventually to real time. Usually when we talk about real-time performance, we're talking about roughly 10 frames a second. That's sort of the boundary between something that's interactive and something that's not interactive. If you're playing a game, I understand you want 60, 100 frames a second. Those are sort of the frame times that people expect if you want to be able to interact with it really in a real-time setting. But 10 frames a second, at least you're going to be able to interact with it. I don't know if you'd want to play games with it, but you're manipulating models on a screen. That's something that's realistic. So, these, at the time, Herbert the teddy bear here, who has this wonderfully beautiful fur, he was the most complicated object that was ever rendered. And it had a supercomputer that took, I think, almost a day to be able to do it. This was done at Caltech. Today, that's something we can do, this is like 20 years later, but we could do pretty much at a real-time setting. Okay? And that's fun. It's really cool. I think about if I was to become an auto designer. Well, first, I'd probably be out of work right now. But you're a hero if you can make things run, 2% better. Hero. Okay, if you get 2% better, that's wonderful. Well, one of the fun things about what we do is every year it gets 50% better. And you can do things in your lifetime that you never, that you never thought were possible, and then 20 years later, you can actually make them happen. So that's tons of fun. Okay, so this sort of thing gets better, but we still have a really long way to go. Long way to go. So there's lots of sorts of effects that we're just not very good at right now. This is a ray tracing. It's like 10 years old. Matt Farr drew this, and he'll be one of our guest speakers this quarter. But if we look at sort of the cool things here, one of the things is sort of this light transport here. Right? There's light outside there and a little crack in the door. Okay? That's something we don't really deal with right now. If you look at sort of the texture on the floor here, this is actually modeled. There's lots of bumps and nooks and crannies and cracks there that are actually done correctly, as opposed to what would happen in a game today where things would be flat and you'd kind of fake the way that looked. If you look at the shadows here, like behind this is a soft shadow. Okay, well, shadows generally are soft, and what you see in games are harder shadows with hard edges. Okay, it's hard to do soft shadows accurately and well. Okay, not very common in games. The sort of copper texture on this, that's a very complicated copper texture. So, we can make it look pretty good today, but it's not going to look as good as this. So just, some examples. I happen to like the picture, but, there's lots of things we do in this that, this is going to take hours to render that you can't really do in real time today. So there's lots of things we'd like to be able to go. How long does it take to render a Pixar frame? Roughly. Okay, one frame of one Pixar movie. Okay, just an hour? Okay, so that's like the right order of magnitude. The right answer is evidently 3 hours. From the time Pixar started, it took 3 hours to render a frame. And every generation, they get better machines, these new algorithms, and then the scene gets more complicated, and it still takes 3 hours to render. Okay, so whenever anybody asks you how long it takes, 3 hours. So the difference between 3 hours and a 60th of a second is really large. Okay, and maybe in a few years we'll be able to do Toy Story real time, but we're still a long way from being able to do WALL-E real time, because things have got amazingly better over that time in terms of the way Pixar does things. Okay, Aldi Ray Smith used to say that reality is 80 million polygons, and that's per frame. So he was one of the founders of Pixar. He actually made up the name. And so that's just a lot of polygons to be able to render per frame. That's down to the Nyquist limit, where every pixel has 2 polygons. And he's assuming 2,500 by 4,000 resolution, which is roughly what film has, and a depth complexity of 4. So you're drawing 4 things at every pixel. Okay, that'll give you 80 million polygons. And you want to do this 100 times a second. That's an amazing amount of compute. It's far beyond what we can do with the GPU today. Yeah.
So 80 million versus real time. What would that be?
Let's see. For realistic, boy, I would bet we could do on the order of 1 million or so and be able to do it 100 frames per second. So probably 1 to 2 orders of magnitude different from what we can do today. But also keep in mind each of those polygons is going to have programmable processing that's much more complex than we do today as well. Okay. So now I'm going to sort of walk through the class and sort of talk about what we will be talking about. Sort of the prereqs to this class, I say, are an architecture class, and that's really a must. It can be at the undergraduate level, but you have to have had some architecture. And I really encourage people to have graphics, at least at the undergraduate level. Here, that's ECS 175. But I always get people in this class that haven't had any graphics. So I would like to, if people are interested, spend probably an hour and a half to 2 hours showing OpenGL code and eating pizza after class on Thursday. So basically, Thursday's lecture is going to be why OpenGL was built the way it was. Okay, what are sort of the design choices that they made? And what I want to talk about here is sort of showing OpenGL code and being able to walk through the code so that you know how to recognize it. It's not important you can write OpenGL code in this class, but you have to be able to understand and edit OpenGL code in this class. And so I want to show how that's actually done. And Thursday's lecture plus this will hopefully give you a 1-day intro to graphics, and we'll let you understand it.
Is it possible to change the time of the tutorial because the operating system class is after this?
Okay, I can do this like at 6. Okay. So how many people would be interested if I did this at 6? Okay. So, all right. You kind of know OpenGL, though. Okay. I will send a note to the class. How many people have a conflict at 4:30? Are you the only one? 1, 2, 3. Raise your hand high. If you have a conflict at 4:30 and you're interested. How many people have a conflict at 6? Oh, you guys can't prove. All right. Yeah. All right. How many people are interested at 4:30? And sorry. All right. How many people would rather? Okay. Don't raise your hand if you don't want to come. How many people want to come at 4:30? How many people want to come at 6? Okay. I got to go 4:30. Okay. I will be there at 6 because it'll be a couple hours. We can sit and chat afterwards. We'll get pizza at like 5:30 or so. I will email and get RSVPs here. Sorry, I haven't had that sort of conflict before. Okay, but if you already have OpenGL experience, I mean, this is very basic, so go ahead and skip it, and you're welcome to come if you want. So when I send email to you, let me know if you're interested in coming. Okay, so what I will talk about is the rendering pipeline in general. And so I want to make sure that you understand the pipeline, what the stages of the pipeline are, and so on. And so I will talk about sort of why OpenGL is built in the way that it is, as an example. So we have lots of choices in how we build a hardware pipeline. We're going to sort of talk about the different choices we could make, and then what something like OpenGL actually did. Next lecture, I'm going to talk about performance characterization. So this is a graph I show sort of on how do you decide what the bottleneck is in a graphics application. So it's kind of a cool, set of things to do. But we'll talk about how do you characterize performance? What are sort of the things that you look at? How do you measure it? That sort of thing. Next lecture, I'm going to talk about the programmable pipeline. So OpenGL and DirectX, to some extent, are largely fixed function pipelines with maybe a little bit of programmable parts. And so I'm going to talk about the pipeline from the point of view of programmability. So what do the programmable standards look like? What do the APIs look like? What does the hardware look like to some extent? So it's sort of an introduction to to that sort of aspect of graphics. I'm going to spend 2 lectures on general purpose programmability of the GPU. So how do we use the GPU to solve things that are not graphics? Okay, so how do we use the GPU as a general purpose processor? So this is what my research is on, so I got lots of things to say, but hopefully that'll be interesting. I'll spend a lecture sort of on the hardware parts of things. So why is graphics hardware fast? Okay, what are the techniques that it uses? And we'll sort of talk about modern VLSI kind of trends and how GPUs take advantage of those. Okay, and then we're going to spend 6 lectures talking about the details of the graphics pipeline. So here's sort of a high-level graphics pipeline. What happens as you render something? Triangles start up here, they go down, things happen to them, you come out with pixels. Okay? There's lots of stages of this pipeline. And so we'll talk about what happens in each of these stages and what the algorithms are and the hardware structures inside that. So I'll spend a lecture on geometry, lecture on rasterization, lecture on texturing, lecture on composite and display. I can't fit that all into 4 lectures, so it ends up being that I'll fit these 4 lectures into 5. And then I'll spend a lecture juggling the pipeline. So what happens when we take this pipeline and we take it in a different order? Okay, what happens if we make other design choices? So one of the things I'll talk about is, say, Pixar's pipeline. Pixar uses a different pipeline. It's called Raise. So we'll talk about what that pipeline looks like. Why did they make the decisions that they did? As time goes on, we're moving away from, we're sort of the state of the art now. All right, before this was sort of this fixed function pipeline had some configurability. Right now we're into an era where some of these stages are very programmable, okay, but it's still a fairly fixed pipeline. Where graphics is going is toward a programmable pipeline where you can take these things and juggle them and put in new stages and delete stages you don't need and so on. Okay, the programmable pipeline. It's very exciting, and I want to be able to show what some people have done before as far as the way they've structured their pipelines. So anyway, hopefully that'll be cool. And then my last lecture is going to be on parallelizing the pipeline. So this uses a lot of historical kind of machines. Sort of SGI's reality engine is 1992. So you have one pipeline. Okay, and hardware. What happens if you want to make it twice as fast? You have twice as much hardware. What happens if you have 2 chips? How do you parallelize this thing? Well, it's not trivial. And so we'll talk about different ways that you might want to think about parallelizing the pipeline. Okay, so that's 13 lectures total, including today. Actually, it's 14 lectures because I have that extra spill lecture. And then we have 5 guest speakers. So these are all going to be on Thursdays. They'll be weeks 5, 6, 7, 8, and 9. And these are great people, and I'll tell you about them now, that are going to come up and talk about sort of graphics trends. They're, I think, all from 4 industry, 1 academic. People that really know a lot about this stuff. So Matt Farr is going to come from Intel. He's going to talk about Intel's latest GPU. It's called Larrabee. This is very interesting new graphics trend. They just talked about this for the first time this past summer. Sort of some hardware details of it. Intel's very interested in getting into the GPU business, and they've taken a very different approach than historical GPUs have. It's a very software-centric approach. This runs x86 code. It's cool. It's a really exciting piece of graphics hardware, and Matt's going to come up and tell us about it. Next lecture is also from Intel, Aaron LaFawn, and so he's going to talk about a little bit more on the software side, this idea of programmable graphics, that you have, you don't just have a fixed function pipeline anymore. Now you get to do different things in your pipeline. You get to juggle it. It's something Larrabee's actually going to be really good at. The question is, how do we actually use that? So Aaron works up in Seattle. He's actually my first PhD graduate, so I'm very excited to have him back here, but he knows this stuff really well. So I'm excited he'll come give us a talk. John Nichols is coming from NVIDIA. John is the director of architecture at NVIDIA. So he has a real parallel computing background. He's the chief designer of NVIDIA's latest series of GPUs. So the G80, the GeForce 8800, those machines that are CUDA capable, that are capable of doing this general purpose stuff. He's the main guy that designed it. He's never been to Davis, so I'm very excited to have him up here and give a talk on this stuff. Justin Hensley is going to come from ATI. Couldn't find a picture of him, sorry. So he's doing a lot of GPU computing stuff, but also has done some architecture on these latest chips. He's actually a Davis undergraduate and then got his PhD at North Carolina. And so excited to have him as well. And then Jeremy Sugarman is going to come from Stanford. And so Jeremy is designed an abstraction for graphics pipelines called GRAMPS. And this is recently published in ACM Transactions on Graphics. Really bright guy. And so I'm excited to welcome him to talk about this stuff. So every year we have guest speakers. I'd like to really encourage you to come on those days for sure. I'm boring, but these guys are awesome. Be really attentive and ask a lot of questions and challenge them when they're here. So part of what they're going to be doing is, trying to sell you their vision. The Larrabee guys are going to try to tell you that, this is the way we should build GPUs. And then John Nichols is going to come and say, well, what NVIDIA is doing, this is the right way to build GPUs. And so to some degree, they're trying to, market to you. And you should be challenging their assumptions and showing them how much you've learned here, but really showing them that Davis students are great and bright and they want to hire you when you get out and so on. So I will appreciate especially your enthusiasm and participation on those days. So these are all scheduled. Actually, we have all 5 of these guys scheduled. So that's all on the website. The last lecture is project presentations. Like many graduate classes, you will be making up a project and then presenting it on the last day. If we have this many people take the class, that's a lot of projects. So you'll get to give a talk in 5 minutes. And so we're going to do that on the last day. We'll take turns doing our projects and showing them to the class. So that's always enjoyable, and everybody comes up with really creative stuff. So I'm looking forward to seeing those. OK. Any questions on sort of the outline? OK, well, I'll finish off with all the administrative stuff. So just to start with sort of what I'm expecting that you will have computer architecture and computer graphics knowledge. This is not vital, but when people ask me about how much graphics should I know, I say, well, you should have spent your Christmas break learning it, so it's too late for that. But the first assignment that you will be doing is going to make sure that you will know at least the basics of computer graphics by next Tuesday. So if you haven't had any graphics, hopefully Thursday afternoon's lecture will be useful for you. But also, you'll definitely have to do a little reading to get up to speed. And this is not a course where you'll learn basic graphics. reasonable familiarity with doing programming in general, and I'm not usually worried about that. I've always taught this course for 3 units. I don't know if it's a variable or not. If anybody really wants variable units, like take this for 1 unit or something, we can talk. I don't know if that's possible. I always offer, but nobody's taken me up on that. Okay, we don't have a textbook required. There's some really good books. I have links on the syllabus about this. I know at least a couple people have bought this new real-time rendering, which just came out a few months ago. It's probably the closest thing to what we teach in this class. There's lots of good techniques. They have a lot of software stuff that I'm not really going to cover. But there's some really bright guys that wrote this book, and they have a very good website with tons of great links on it. So it's a good place to start. You'll probably want some OpenGL tutorial and reference kinds of things. There's some really good online resources. The book that's really useful is the Red Book, which is the programming guide. But you can find that online from some site in Hungary. And so you don't have to know like the latest and greatest OpenGL. Just sort of standard OpenGL 1.0 is fine for this. There's some other good books that are interesting for project ideas and so on. So these are just books I like and recommend. There's links to all these on the website. Okay, so we're teaching a TV class. The reason this is a TV class is that we have the Citrus initiative that's over 4 UC campuses, and they're interested in doing some broadcasts of classes to other campuses. So the people at Berkeley and Merced and Santa Cruz can see this class too. The reason I like this is I like teaching in these TV rooms. It's close to my office. They're good rooms to teach in. So cool by me. Good to have things taped. If you miss class, I guess there's a webcast. So if you sleep in past 4:30. At least you'll be able to see this. I really encourage you to come. I try to have interactivity, and it'll be more fun if you come, and there's no way I want to lecture to an empty room, so please do come to class. But at least it's possible to make it up if you're not there. We're not necessarily going to tape all the guest speakers. Sometimes they say things they don't really want out in the real world for the world to see. People definitely look at my lecture slides and watch these and look for nuggets. So some of the speakers say, we'll just make this class only. Please talk into the mics, and the camera operators back in the back there. I understand it's been used graduate students. Thank you. You guys are great. All right. I hope you enjoy the material. Learn something. No exams, no notes. The important thing is you come to class, listen, and participate. And please do participate. That's important to me. I will post slides after every class on SmartSite. So just in the resources section, I'll just make a PDF of these and send it up. Okay, so just to know what's coming up as far as assignments go. Okay, so in SmartSite, you can set a profile picture. I would like to learn your names. I can't do that if I don't see your pictures. So please, by tomorrow, go set your SmartSite profile pictures. If you don't do this, I will ask for you in name in class, and that'll be embarrassing for all of us. So even though I know some of you, and you know that I know you, you all have to set this. And then I can look at them and see everybody's profile picture with a name. And I will put this in my email reminder today. So it's real easy to find. You log on to SmartSite. There's a profile button on the left side. You can set your picture. I really appreciate that because I do want to learn names. Okay, assignment 1 is due on Tuesday. It is on the website, on the SmartSite under assignments. But what I want is a 3-page paper on the graphics pipeline written for the layman. Okay, so I want you to explain what the graphics pipeline is. And I want it to be written for the layman, meaning a non-technical specialist. It will likely be graded by a member of my family who doesn't know anything about computers. Depends on who I can bribe to do it. But it's good because you get to practice writing. Okay, and people don't write enough as engineers. It's good because you get to practice writing for the layman, and it's a very important skill. You want to be able to explain what you do to somebody that is not in your field. And it's really good because those of you that don't have a graphics background are going to have to rapidly come up to speed to be able to write this sort of thing, because to explain this to a layman is even harder than explaining it to somebody in the field. So 3 pages. I have guidelines as far as font sizes and margins and so on. It is not very – you will want more room than you have. So you have to really think about what you're going to write. Okay. Assignment 2 is going to be characterization of graphics hardware and or GPU hardware. And so we'll talk about this later on. But in general, what I want you to do is do some measurements with graphics cards. And you can either choose to do measurements that have to do sort of on the graphics side, or measurements that have to do on the GPU or GPU computing side. So for instance, I want you to characterize triangle versus fill rate. Okay, so When you have really big triangles, you're spending all your time filling those triangles. And so the fill rate's going to look really good, but the triangle rate's going to look really bad. If you have little tiny triangles, you spend all your time doing the geometry part. And so you're going to have this great looking triangle rate and this really bad fill rate. And so what I want you to do is characterize that. Okay? And there will be more details. I'm just sort of giving you a highlight of what's coming up. So this is going to be due in roughly a month, so I guess 4 weeks from now. I've added, you sort of have a choice of doing either a graphics side or a GPU side. Now, one of the nice things is if you don't have a graphics card, I can lend you a graphics card, and I have a whole box of G80 class cards, which are NVIDIA CUDA-capable cards. They're sort of the cheapest CUDA-capable cards, but I am happy to lend those to any of you for the quarter, both for this assignment and for any project that you want to do. In particular, if you're doing a GPU computing project and you don't have a CUDA-capable card, this is a nice deal. So it's a I guess, PCI Express card. If you don't have access to that sort of machine, then we'll talk, and hopefully we can figure out something that'll work for you. But don't be in a hurry to get the card, but I'll be happy to lend those out because I've got 11 of them, I think. Eventually you'll do a project, and this is sort of the main part of your course, of your grade. You will pick what the topic is. I'd rather have a narrower project that you finish rather than some broad thing that you only hit some high points of. There's plenty of opportunity to get feedback from me. You will do a pre-proposal where you just sort of write a couple paragraphs about what you want to do. I will reply to that. You'll write a formal proposal. I think you get 1 page. I've got guidelines for all these things. I might require revision, and then by the last day of class, you will both be ready to give a talk and do a report. So I will have things that I will bring up throughout the class as far as this looks like an interesting project, or we don't really know about this. Mostly I want you guys to pick something you're interested in, and I'm very open to different things as long as it uses graphics hardware in interesting ways. We're going to use some software resources. NVIDIA CUDA is what a lot of people have used recently. This is a GPU computing environment. There's a number of GPU computing environments that you can use. For the benchmarking assignment, we have sort of some OpenGL scaffolding code that you can use and instrument to do some benchmarking. We can get some, there's lots of different pieces of software that you can use that might be interesting for this sort of class. In general, you're giving me things that are write-ups. You're not giving me code. Okay, you're going to write a 3-page paper. You're going to write a report, and that's what I'm going to grade, both for the second assignment and the third assignment. So what I really care about is intellectual merit, and so I'd like you to emphasize that in what you do. Also, unlike in the real world, it's okay to fail. I mean, you can do this ambitious project that just doesn't work out. You can learn that, hey, this turned out to be a really bad idea. What's important is that you understand why it's a bad idea, and you're able to convince people that it's a bad idea. So in the real world, you need to succeed, and people don't report things that fail. It's okay in this class to fail, but I want you to learn something if you do. Okay, so here's what I'm expecting. I really want you participating. It's going to be a more fun class that way. I've appreciated the questions I've got today. I try to have a really interactive style. And we'll have a better class if you do. So please answer the questions that I ask. Let's look into some interesting topics. Definitely challenge the guest speakers that come. That's important. So the most common problem that I see, and this is especially true for undergraduates, but it's also true for graduate students that haven't been here very long, is the not getting started problem. So when you're an undergraduate, basically what you learn is that any assignment can be completed if you start at 9 p.m. the night before and have enough caffeine. Okay? Nobody's going to give you anything that big that you can't finish by like 9 a.m. the next morning. If you end up starting your project 3 days before it's due, you're not going to finish. Everybody else in this class is going to start the project in the middle of February and spend 4 or 5 weeks on it and get some really interesting results. And so part of the reason I'm asking for a pre-proposal and a proposal and so on is to get you thinking about what your schedule is going to be. But the most common way people don't succeed in this class is they just don't get started doing anything, and they start too late, or they don't decide what they're going to do until too late. And so I want you to think about from day one the sort of projects you might be interested in and be talking to me about it. And those are the students that really come up with some neat stuff. So final slide, I really do welcome feedback. I'm still learning how to be a better teacher. And so feedback on the sort of lecture style, any of the things that we're doing in this class, I really do welcome them. I take criticism well. And you guys have been students a lot longer than I've been a teacher. So I'm really happy to get your feedback there. So I've got my office hour, although that's actually Tuesday, right? Today's Tuesday. But experience says email for appointments and drop by, and if I'm there, I'm really happy to talk to you. Okay, yes?
So the software list you had for completing the assignment, is that Windows-only stuff?
Most of it's source code, so I think it'll run on just about anything. I know the GL code will generally run anywhere. That's part of the reason we use OpenGL in this course instead of something like DirectX. So generally most of the stuff I showed was pretty solid.
Writing stuff is just done by just LaTeX or?
I love LaTeX, so I'm really happy if you use that. Word's fine.
So what kind of format do you have?
PDF is usually the easiest thing. So please submit things in PDF if you can. I know I can read those anywhere, and I don't have to worry about Word macro viruses that are getting in the way. So yeah, PDF is preferred as far as your output format.
Professor, can you give an example of a good project and a crummy project?
Okay, let's see. Let me think of some of the, okay. All right. So first, some people are going to want to just do your research. Like you're going to say, I'm working on research in X, whatever X is, and I would like to do a project exactly in X that's exactly on this project that I'm going to work on anyway. And I would encourage you not to do that if you can. And the reason I say that is because, when you get into the real world and you have real jobs and stuff, they're going to want you to work on your job all the time. And you're never going to have the time to do really cool sidelights and explore something that you don't know a lot about or something that you're just interested in. So this gives you the opportunity to be able to say, I really don't know much about X, but I think it would be a good project and I could learn a lot if I did a project in that. So, I will accept projects that are your research and you were going to do anyway, but I think from a student point of view, it's good if you go out and do something cool. Recently, we've been doing a lot of GPU computing projects. Last year we had a group that did a neural network, which was really cool. I hadn't seen that on a GPU at all. We had some cryptology kind of stuff that I thought was interesting. We had some data visualization things where people took visualization kind of kernels and moved them onto the GPU. In general, I want things that help you learn more about the hardware. And I want to see things that where you can quantify to some extent and say, hey, I'd like, here's what I see as the real bottleneck in the hardware. And I can quantify it, the fact that this is the bottleneck in the hardware. And that could be, a performance bottleneck or a programming system bottleneck and so on. But where these are the things that I would do to remedy that. I wish graphics hardware would do X, and I would like to be able to, if I was building the GPU or the programming system, this is the sorts of things that I would put in. So I think some of the interesting things have been when people have had domain-specific experience and are able to meld that with GPU kinds of stuff. So I've really enjoyed those sort of projects. I've also had projects where people have looked at different aspects of the GPU and said, hey, how do I do X? So X at one point was noise. Okay, so noise, one of the complaints about computer graphics is, oh, it looks too good. Everything looks shiny and nice and new, and real things have dents and scratches and so on. And so you can use a little bit of randomness in your rendering, and in graphics that's called noise, and add that to the rendering process and make things look better. And so if you look at Pixar RenderMan, that uses noise all over the place, and things look more realistic when you put in a little bit of that randomness. How do you support noise in hardware? Okay, so I had a really good design for how I thought that was coming. I would say that when people do really broad stuff, it doesn't look good if you don't cover it. So that's been a mistake where it's like, if you have all these obvious questions at the end, that usually doesn't work out very well, whereas I'd rather have you look at something a little bit smaller and really trying to cover it better. But it's more in terms of the effort you put into it. I think that, I want you to pick something that you're excited about. So, and I will talk about things. So one of the projects that would be ambitious that I would love to see that I talked a little bit about with graduate students was we have this programmable interface, this CUDA from NVIDIA, and it lets you program these GPU kind of applications. Can you write a graphics pipeline in CUDA? Right? Can you use the general purpose interface to implement the entire graphics pipeline? How do you do that? Okay, so that's really, so it's a very tricky way to use the graphics hardware, but it would be very interesting to see how that would be done, because maybe that's how it will be done in 10 or 15 years. So I'll be bringing things up that I think are interesting. Does that answer your question?
Yes, thank you.
Okay, I'll see you guys Thursday.